I want to maybe talk first about this Morse Index characterization of self-shrinkers. Right, so I want to talk about sometimes the second variation of this Gaussian surface area. Okay, so again, the setup is we fix a self-shrinker. So this is, of course, a critical point of f. So we can look at the second variation of the f functional. And as usual, the observation is that the important variations to consider when computing the second variation are the normal variations, since tangential ones don't change anything. And as is always the case, everything is much simpler when we're in a two-sided case in codimension 1, because then we can reduce it to essentially a scalar problem. Right, so remember, here we know that, it's a fact because it's proper that sigma is two-sided, or we make this as an assumption. So we fix a normal n sigma. And the idea is we want to consider compactly supported normal variations. So the idea is you fix a function u in, say, C infinity compact support of sigma. We always want to consider compact variations. And we let sigma t be the normal variation. So it's a set of position vector of p plus u of p times the t. Right, so again, the picture is supposed to be here's sigma, and then we would have right, so there's some function. This is p times u. So there's a function here that changes sign, and that's our sigma t. Okay, so it's a standard computation, though an involved one, to see that we want to look at the second derivative of the Gaussian surface area of sigma t. One works this out to be okay. So this is there's this weight factor here, which of course has to be because we're considered weighting volume. This is what you would expect from the second variation formula for area. And then we get this extra minus the half term, which again has to do with the weight. So this is, if you like, this has to do with the fact that somehow the Ricci curvature of the Gaussian soliton is positive. Okay, so we observe, of course, that this is a nice quadratic form, and of course we can integrate by parts, and this is the same as saying that it's the minus. Let me write it this way. Right, where here L sigma is this sort of linearized curvature shrinker operator, which is L Laplacian of sigma minus the sort of drift term, which comes from the weight. So when you do the integration by parts, you pick up this drift term. And then there's the curvature term, and then this 1/2 term. Okay, so this is our operator we want to consider. And sometimes it's convenient to write this as we observe. It's a quadratic form, so we're just going to write this as q sigma of u. Okay? And the point is, as we know, of course, the sort of second variation properties of this function are then going to be closely related to the spectral properties of this operator, which we will exploit. Okay, so what is the Morse index? Right, so we define the Morse index, we define index of sigma. This is basically equal to the dimension of, let me say this is the sort of maximal dimension of a subspace of C infinity compact sigma on which this quadratic form Q sigma is negative. Right. So of course, we expect somehow, we're interested in understanding which directions decrease to second order the F functional and which directions increase, and because of the nature of, it's standard that the index is, of course, the directions that decrease it, and the maximal dimension. So how many kind of linearly independent directions can we decrease the functional in? And right, the point that this is always a finite number is clear when it's compact somehow by spectral theory. But in fact, because of the way the weight is, it's actually always finite for reasonable sigma. So I'll get into that in a little bit. But one observation, of course, what makes is, again, when sigma is compact, you can always plug in the constant function 1 and see that you've got a negative direction, and that's compactly supported. Alternatively, if it's non-compact, because this weight decays so rapidly, you can sort of cut off 1 very far out, and the energy you gain from the cutoff is negligible. So in fact, you'll also get that a negative direction. So the index, at least, is always at least 1. Just a sort of a trivial observation. So in other words, like minimal surfaces in the sphere, there's no, we're never asking for stable guys, value guys with index 0. We're trying to find things where the index maybe is low. And as I said, of course, there's a relationship between the index of sigma is related to the spectral properties of L sigma. So again, roughly speaking, and this is very easy to see when it's compact, and again, using kind of cutoffs, you can also prove it when it's non-compact. Basically, if we let V sub minus inside of, say, C infinite functions of sigma intersect some weighted L2, right? So remember, this natural kind of L2 space here has this Gaussian weight on it. Be the space of eigenfunctions of L sigma with, or let's say minus L sigma with a negative eigenvalue. Right, so if you think about it, if you have an eigenvalue, if you have an eigenfunction of minus L sigma with negative eigenvalue, and say sigma was compact, you could just plug this in and get a negative variation. Of course, if it's non-compact, there's no reason for the eigenfunction to be compactly supported. But you can prove that if, again, when sigma is reasonable, which is basically everyone will ever consider, the eigenfunction grows at most polynomially. So the eigenfunction grows polynomially, the volume of sigma grows at most polynomially, but this weight decays very rapidly. So in fact, you can cut things off, just as I said, and get the same sort of idea that it basically, the index of sigma is the same as the dimension of E minus. Okay, so so what we want to try and again, this is obvious when, again, the one inequality is obvious when it's compact. The other one you have to use the kind of min-max characterization of eigenvalues, but it's obvious when it's compact. But it's not much harder when it's not compact. Okay, so we're going to exploit this in a bit, but the idea now is we want to understand what are the surfaces, the shrinkers with a low index. And the first observation we make is just, for example, what is the index of the hyperplanes? Well, that is 1. So that's actually, it has to be at least 1. It turns out it's 1. It's achieved. And again, what is this sort of function that achieves that? Again, it's roughly something like translating vertically. Of course, that's not completely supported, but you cut that off, and it's fine. Another example is, of course, the index of Xn, square root of 2n. Right, so that turns out it should be n plus 2. Okay. So the idea here is, of course, well, what are the negative directions? Again, these are all going to be geometric. So if you take this round sphere and you dilate it by making it a little bit bigger, that's going to decrease the F area. Again, because the way the F area works is there's sort of, as you look at the spheres, a very large value, it's 0 because the weight is so small. A very small radii, it's 0 because the area of the sphere is 0. So there's some, as you increase the radius, you kind of go from 0 up to some critical value and back down. So that's why you get a negative direction there. And then similarly, if you move it off the origin, you sort of uncenter it, which there's n plus 1 ways to do that by translating, that also decreases the Gaussian area. And those are and taken together, those give you all the possible ways of decreasing the index. And we observe that these are basically both very geometric in some sense. It's clearly geometric here. Here you have to do a cutoff, which makes it a little trickier. But, so with this in mind, we then have a following theorem, which essentially was written down by Kolding and Minicozzi.
Cylinder is less?
So it turns out that, and this is sort of interesting, so if k is between so this actually also is n plus 2. But this is a little trickier because, right, you might think, well, there's these translations, but you can't, you have a translation invariance, so that doesn't give you a negative direction. So it turns out that I'll get this in the course of the proof, there's some non-geometric eigenvalues with negative eigenfunctions. Okay, so so it turns out that this is actually the whole list of these low index guys. So in fact, this theorem, so that the only smooth two-sided, again, this is implicit in our definition, but I'll mention it, self-shrinkers with the Morse Index. Are the generalized standards. Okay, so I want to give a kind of idea of the proof, which is essentially, I'm going to maybe gloss over a few details, but Okay, so again, one of the things I'm going to use is that sort of, and it's again trivial when you're a compact shrinker and you have to think a little bit, but it's not that hard when you're non-compact, is that this stability operator L sigma actually has discrete spectrum when you look inside of these sort of weighted spaces, the appropriate weighted spaces. So that will be used. Okay, so then basically the idea is, as I said, we want to sort of come from this perspective and argue that on any shrinker, somehow these geometric deformations, which is corresponding to scaling in some sense or translation, are always going to be eigenfunctions of the stability operator as long as they're actually there. So that's a kind of computation, but one can compute. Again, I probably won't do this because I'm lazy, but if you compute the L sigma, you fix any vector, any fixed vector in Rn plus 1, and you compute the inner product of x naught with the normal and apply the stability operator to it, then you actually get 1/2 of. Okay. So in other words, these guys are eigenfunctions as long as they're non-trivial, with eigenvalue 1/2 of L sigma or minus 1/2 of minus L sigma. So specifically, if we let, say, Fi be equal to the inner product of Ei with the n sigma, this is okay, so that, and again, if you're compact, then this is immediate from this computation. Of course, if you're non-compact, you have to do very little work, but a little bit of work to check that it's actually in the right space. But that's actually, again, clearly this is a bounded function, and so then, this exponential weight is definitely, as we can claim, is that the volume is growing most polynomially, so this definitely dominates that. So you're good. Okay, so that's the translation direction. Okay, so this is again something a straightforward exercise, but one I won't do. In a similar fashion, if you look at the mean curvature, which of course for a mean curvature is just, it's worth saying the mean curvature is the same as the position vector dotted with the normal vector, right? That's what this is the scalar mean curvature. This is the equation basically tells you this. So you can think of it either way. So I find it easier to think of it in terms of the mean curvature. You can compute that the mean curvature of H sigma is equal to H sigma. So this uses, say, Simon's equation. Alternatively, you could have used this, try and compute it here, and do basically the same types of computations as you get there. So in other words, again, if this means that if H sigma, say, is non-zero, then it is an eigenvalue of minus L sigma with eigenvalue. Right, so, okay, and again, this is clear if it's compact. If it's non-compact, then again, by this identity, you're growing it most linearly. So you're again in the weighted space. So you're also an eigenvalue in the non-compact case. Okay, so how does the proof go? Well, the point is, we need to make sure, if we just count up these eigenfunctions, if everything is linearly independent, then we have n plus 2 of them, and so there's no other possible eigenfunction under this index bound if we believe this identity here. So So let's just suppose sigma is compact. Just prove it here, which again is the simpler case. So in this case, of course, if you're compact, no minimal surface is compact, so this implies that h sigma of p is not equal to 0 at some p. Right, so we have an eigenfunction with eigenvalue -1. Similarly, right, let's just think about it. So what could happen? Obviously, these are different. These are eigenvalues with, eigenfunctions with different eigenvalues. So there's no linear dependence relation between these two guys, this hi and any of these. But suppose there was, suppose that we had a linear dependence relation. Right. Of course, going back to the definition, that implies that somehow there's a vector c which is not 0, so that c dot n sigma is equal to 0 on sigma, right? Which in other words implies that sigma sort of splits as a line of sigma prime across some r, right? So there's right. If you have a constant vector that's tangent everywhere to the surface, then clearly it's invariant under translation in that direction, which of course, this can't happen. When sigma is compact, right? Right. So that implies, of course, that the dimension of v minus is greater than or equal to. Well, let's just put it this way. V minus contains the span of these functions, h. Right, so in particular, these are all linearly independent, so the dimension of V minus is greater than or equal to n plus 2, but of course it's supposed to be the same as the index, which in this compact case that's trivial, so that actually is equal, right? So they're equal. Okay, so that means we found every eigenvalue, every eigenfunction of L sigma, minus L sigma with the eigenvalue negative, and this in particular implies that minus 1 is the lowest eigenvalue of minus L sigma, right? So that, of course, there's a very important property of the lowest eigenfunction when it's scalar, and that is that it's unique, and because it's unique, it actually has to have a sign. So, right, so this implies that h sigma is not equal to 0 anywhere. Okay, so in particular, it's mean convex, right? Okay, so then it's mean convex, and so then we know the classification of mean convex self-shrinkers, and that it's compact implies it has to be the round sphere. Okay, so that hopefully makes sense. Everyone familiar with this fact? And again, this is the part where you really, you're using that you have a scalar very crucially. Okay, so that's the compact case. So of course, if it's not compact, you can't. You have to do a little bit more work. So let me just make some remarks there. So sigma is non-compact. Right, so the first observation is 1. If the mean curvature is identically 0, right, then that implies by the equation that sigma is a cone, right? But in fact, it's a smooth cone by assumption, right? So that implies that sigma is a plane. So right. Remember, because we're using the equation here to see that it has to be a cone when you're minimal, and since it's smooth, it's a plane. Okay, so without loss of generality, h sigma is not identically 0. So the second observation is, of course, right, if sigma doesn't split, then we basically have that the dimension of v minus is greater than or equal to n plus 2, right? Because, of course, the point is v minus is going to contain h sigma, which is not 0 because we're not in the first case. And all of these f1 up to fn plus 1, right? The span of this. Okay, and these guys are all linearly independent, so then v minus is bigger than n plus 2, and hence, again, believing this notion with cutoff, it tells us the index, these are everybody, this is every eigenfunction. And again, you have to believe that this works even with the cutoff, but really the proofs don't change at all. This actually, again, implies h sigma is positive. So this, again, is positive, right? Because it's the lowest eigenfunction, which then is a kind of contradiction, because then it has to be a generalized cylinder. Right, so it's a contradiction. Okay, so now, in case 3, where suppose sigma splits as sigma prime cross r to the n minus L, and here we assume L is strictly positive, since if L was actually 0, then we would be in this case, right? So sigma prime is non-trivial otherwise. So. Okay. Right, so we're in the splitting case, and then the idea here is that, and let's suppose this guy now is, can't be, let's suppose this is the maximal splitting. Okay, so then the idea is, again, if we look at the mean curvature of sigma, which of course is really just the mean curvature of sigma prime, since there's no curvature coming from the translation in variant directions, is non-vanishing, since we're not in case 1. So this guy is an eigenfunction. Similarly, if we look at f1 up to fl plus 1, right, these guys are all sort of linearly independent. And so, again, eigenfunctions. And the point is here, finally, right, this is not, if we take these together, we don't, we could imagine there's other eigenfunctions we didn't know about, so we don't necessarily know this is the lowest because there might be one below it. But we actually can define, we define GL plus 2 is equal to the mean curvature of sigma prime times the coordinate vector of x L plus 2, and similarly Gn plus 1 is equal to the mean curvature vector of sigma prime times x n plus 1. Okay, so here, right, we're just taking, this is a function that's sort of invariant under translation, right? It's just sort of defined, it's only varying potentially on the cross section, and then this is the coordinate functions in the sort of invariant direction. That's how I'm setting this up. So here I'm thinking of sigma prime. These are like the first, this is like x1 up to xl plus 1. So these are the remaining guys. Okay, so then you can check. Again, these are clearly just linearly growing. They're not very complicated. Right, so you can check that they also are eigenfunctions of L sigma of the GL plus 2 is equal to minus or plus a half GL plus 2. Okay, and the reason for this is, of course, L sigma of H sigma prime is L sigma of A sigma is H sigma, right? But the point is the L, which is no second fundamental form, so L is just the drift Laplacian of the coordinate vectors. This is I believe, also 1/2. Right? That's a simple computation. Just think about, just do it. It's basically because the Laplacian of the position vector is the mean curvature. Right. So that, and the point is the gradient of x, say L plus 2, dotted with the gradient of the mean curvature of sigma prime is of course 0, because they're dependent, they vary in different directions. So if you just apply sort of the product formula, you see you get a kind of, sorry, I have a sign wrong here. Sorry, I think maybe this is minus a half. Yeah, minus a half, right? Because this needs to be, when you integrate by parts, it should be positive. Yeah, so it's this is the. So if you apply the L to this, you get L sigma hits to the product. You get L sigma on this guy. This interaction term is 0, and then there's a script. The other derivatives follow on the coordinate vector and give you a minus a half. So that's where it adds up, and you end up this. And similarly for the other guys. So this of course implies, right, that GL plus 2 up to Gn plus 1 are eigenfunctions of sigma, of L minus L sigma with eigenvalue minus a half, right? So they're also negative directions, and I guess they're kind of, should be clear they're linearly independent, since I mean it's kind of clear. But, so they're also all linearly dependent, and of course also linearly independent from the f's. So then you have, again, by the same argument, which again I'll cut off at some point, you have that because of the index bound, that the v minus is the h sigma, comma f1 up to fl plus 1, gl plus 2 up to gn plus 1. Right, so you found all the eigenfunctions. In particular, implies that again h sigma is the lowest eigenfunction, or minus 1 is the lowest eigenvalue, which of course implies that h sigma is positive, which is again the classification results for mean convex. Okay, so that's how the proof goes. And again, the point about these G's is these are not geometric, right? They kind of are like they almost look like they're trying to turn the cylinder into a cone in some sense, but right, so they don't come from some kind of ambient geometry. Okay, so that's the proof of this index estimate, and maybe, I mean, again, I'm heavily relying on this lowest eigenvalue property. And I'm also, of course, using this classification of mean convex shrinkers. So I may come back to that if you're more interested. So
this Morse Index for this one is sort of also can be formulated in terms of the entropy?
Well, that's a little bit different, so I'm going to maybe get to that. Okay, so this, again, this Morse index is maybe not so interesting necessarily from the point of view of, I mean, of course, in the end, we want to understand sort of dynamics of mean curvature flow, so we want something that plays well with that dynamics. So maybe this concept of Morse index is not quite the right one from that perspective. So Kolding and Nikosi were sort of interested in studying some related concepts, so they introduced some other notions. So they there's this other notion which is called being F stable. Okay. So this is not exactly the same. So essentially the definition here is sigma shrinker in Rn plus 1 is F stable if every variation U, which is sort of orthogonal, which is so again orthogonal in this sort of weighted L2 sense to the span of the sort of the mean curvature of sigma, and then these right. So we have this space of sort of geometric variations, if you like, so the scaling and the translations. So if you have a compactly supported variation that's sort of L2 orthogonal to this, status F stable means that the second variation of U is greater than or equal to 0, right? So in other words, your F stable means the only way to sort of decrease your F area is, in some sense, a geometric deformation. Okay? So this is, again, not quite fully suited for the dynamic point of view, which I'll get to that next time. But they have then a theorem which classifies these F-stable ones, which is a little bit different than the Morse Index theorem. So they prove the following. So they say if sigma is F-stable, then sigma is equal to so you're either the round sphere or the planes, but none of the other cylinders are F-stable in this sense. And again, the basic idea is that the point is you have these negative directions for the F function, or at least as eigenfunctions, but they're not geometric, these G's in the cylindrical case that you don't have in the other case. So the sphere, of course, all the right. The sphere, these are all the eigenfunctions with negative eigenvalue. So of course, anything orthogonal to these guys has a non-negative quadratic form, because it's that's pretty clear. And similarly here. So again, if you want to think about the proof, essentially the idea is that we expect somehow F stable should imply that the Morse index, right, and you would expect this to be true, that if you're F stable, then the index has the index bound we just proved. And then the idea is, of course, the point is that sort of you can then cook up, right? So we won't have to prove this, but if you do prove this, then you're a generalized cylinder. But if you're a true cylinder, basically these GL plus 2, then you can sort of cut them off. And again, because the weight decays so rapidly, if you cut them off outside of a big ball, they're the cutoff. The G's are of course orthogonal to these because they're eigenfunctions. But if you cut it off, it's not orthogonal anymore. But the inner product is incredibly small because of the weight. So it's very easy to kind of perturb it to be orthogonal without making. Since it's it's really definite amount negative. This perturbation won't change the fact that it's negative. So that implies, of course, sigma is a generalized cylinder. If 1 is less than or equal to k. And then you can sort of cut off GL plus, say, 2 and perturb negative direction. Variation sort of orthogonal to this sort of geometric. Okay, so then the main part of the proof is proving this F stable implies index bound. But again, the idea, let's think about it, for instance, in the compact case. So suppose the index was strictly bigger than n plus 2. Then essentially you would have, you'd basically have n plus 2 directions on which the quadratic form was negative. And then by the min-max characterization of eigenvalues, that would mean you would have actually n plus 3 at least eigenfunctions with negative eigenvalue. So that means there has to be at least one of them that's orthogonal to all of these guys. And since it's compact, it's compactly supported, so it's a negative variation, which means it's F unstable. So in other words, if the index is bigger than n plus 2, strictly bigger, and you're closed, then you're F unstable by this argument I just gave. And of course, if it's non-compact, you have to use cutoffs. But again, the idea is the weight is so small and everything grows. Every other quantity is growing so slowly that you can do a cutoff argument and make it work as well. So maybe I won't do the details of that. Okay, so I can either stop here or I can give a very brief sketch of maybe how one might prove this classification for mean convex. I don't know if there's you've probably gone over that, right? So. But I mean, what about the classification of mean convex self-shrinkers? Did you do that?
No, if you want to do more higher codimensions.
Higher codimensions. Well, let me just. Let me just mention. There's a lot of different ways to do it. I'll just give an idea of how to. The basic ideas. So it's right. So again, you prove it using. In the compact case, it's essentially the maximum principle, or the bounded curvature case, it's essentially the maximum principle. In the more general case, you have to do a little bit more, but maybe I won't talk about that. So let me just talk very briefly about the classification. Okay, so I'm going to just give a sketch. Let's suppose sigma is closed and with non-negative mean curvature. Okay. Okay, so obviously this is a special case, but hopefully it has enough of the ideas. So the first observation is, of course, the maximum principle. Implies that if you're non-negative and you're closed, you're in fact strictly positive. So we know that the mean curvature is strictly positive. Again, the easiest way for me to see this is using the parabolic point of view. So you think of the associated flow, and then you just use the evolution equation of the mean curvature and the parabolic flow. Okay, so then, so what we want to prove is something about the second fundamental form, and I'm going to do the following. This is very similar to something I think Ovidio did. So let's let LH squared be the operator Laplacian sigma Okay, so this is like this is defined so that if you have f gradient f dot gradient f g times h squared. Right, so here we're using h as positive. This is the
h squared, like this scale curve.
Yeah, so you're putting the mean curvature squared in the weight. So then this is minus the integral of f LH squared sigma g. Okay. Okay, so again, this is a very similar computation that uses Simon's identity. So again, I'll just say it, but you can compute that if you apply this in operator to this is the second fundamental form divided by the mean curvature.
Mean square.
No, this is the tensor.
Oh, that's tensor.
So this is as a symmetric. This is as a tensor. Then that should be equal to 0 if you set it up correctly. So the application of this is that if you apply it to the square, then that's equal to the covariant derivative of this tensor. Okay. All right. So then, again, because sigma is compactly supported, is compact, right? You can integrate this against this weight, and you get, of course, this integrates to 0 because. So this thing implies, just by integrating, and again, you can adapt this when it's non-compact, but you need to maybe use cutoffs or something. Integrating over sigma implies that so this is parallel. So of course you can then do some more involved computations and see this actually implies it's round. Let me just maybe cheat a little bit and do the following. Right. So since sigma is compact, you can look at you shrink down a sphere and look at the first touching point. Right. So this point P, you take a big sphere and bring it down. So this implies that the second fundamental form of P is it's convex at that point, right? But then, of course, since this is a parallel tensor, right, this should imply that you have a convex guy. So your self-shrinker is convex, and so then if it's convex, then it has to be round. So this implies so. So there, again, the easiest way for me is to think of it in terms of the parabolic flow. So then you're running a convex flow, and it's self-similar, and so by Huysken's result, it has to become the round sphere, but that means you had to start with the round sphere. So this implies... Obviously, there's more to do when it's non-compact, but I don't... So this is by Huysken. Okay, so that's one way of seeing it. That's sort of without doing too much work. But again, you can of course analyze this more carefully and analyze this when it's not compact. But I'll stop here.
What would be the complete non-compact case for the Morse Index? Why Simon's identity cannot be applicable? For the compact case, we use Simon's identity.
For which part?
For the Morse Index.
No, it can be used. I don't.
You can use that as well.
Yeah.
For the complete non-compact case.
For what are we trying to prove?
On the sphere. I thought Simon's identity was something you computed the partial second fundamental form on sphere. Or was that you mentioned, or different thing?
No, Simon's identity is like, for me, it's just the fact that if you know something about the mean curvature, then the Russell-Laplacian of the second fundamental form satisfies it as an equation.
On the sphere,
Well, it's true in
it's general math.
There's a general formula.
the general formula. I mean, it's simplest when it's reasonable. The ambient space is very symmetric. So yeah, there's a formula in the sphere. There's also a formula in Euclidean space. So I'm using the Euclidean space one.
But on the sphere, there's a nice result.
Yeah. It's just yeah. So there's also a result. I mean, in a way, this formula again, as I I said the shrinker shares a lot of similarities with the spheres, minimal surfaces and spheres. So actually these formulas, not this one, but the one the Simons type identity for spheres is very similar to the one for shrinkers. But the difference is in the shrinker case you use this drift Laplacian instead of just the standard Laplacian.